As we discussed earlier, predicting the motion future well using Newton's second law often hinges on our ability to model appropriately interactions of the surroundings with our system. We discussed how to do this already with some specific examples involving forces. For example, the drag force, the force exerted by a spring, and so, from everyday experience, we might expect that there are many additional interactions and corresponding forces that remain to be described. However, it turns out that all of these can be traced down to one of a few fundamental interactions, and we'll discuss one of those now: interactions due to gravity. We spoke earlier about an object's weight in the case of the gravitational force by the Earth on an object near the Earth's surface. Here we'll start with a more general approach to gravitational interactions, and in a few minutes we'll point out how the weight we discussed earlier can be thought of as a special case. We'll start by taking as our system an object whose mass we'll take to be m2. It was Isaac Newton who realized that if there is in the surroundings another object of, say, mass m1, then due to gravitational interaction, the system experiences an attractive force, a force directed toward the object in the surroundings. That force is directed along the line between our system and the object in the surroundings. We'll give that force a symbol, F subscript g on 2 by 1, which is shorthand for the gravitational force on our system of mass m2 due to the object m1 in the surroundings. Let's first work up a way to specify the direction of this force, which depends on the position of the masses, the positions of the masses, since, as we just said, the gravitational force is directed along the line between the two. So, if we make a choice of origin for a coordinate system, then we can locate the two masses with position vectors r1 and r2. Now, if we think about starting at the source of the force, the mass m1 in the surroundings, then there is a vector we'll call r that is parallel to the line joining the masses. The vector r locates where our system mass m2 is with respect to the source of the force m1. This vector r is just the difference between the two position vectors r2 minus r1, or in words, the position of the system minus the position of the source. Remember, the order of the subtraction matters, so let's make sure we double check this. Now notice that r, which is called the relative position vector, because it gives the location of our system relative to the source of the force, doesn't really depend on our choice of coordinate system. We could have chosen a different coordinate system, say like this, and still end up with the same vector r, because after all, how the masses are positioned with respect to each other doesn't depend on the coordinate system. Now, we know how to create a unit vector, r hat, which just specifies a direction, pointing from the source of the force toward the system. If we multiply r hat by -1, then we get a flipped version. This flipped version points from the system toward the source of the attractive force. Just the direction we need to specify the direction of the gravitational force on m2 by m1. Now let's describe what we need to know to specify the magnitude of this gravitational force. This force arises between any two objects with mass, so we would expect the masses m1 and m2 to come into play. Now, experiments and observations tell us that the magnitude of the force is directly proportional to the mass of a system m2, and it's directly proportional to the mass of the source m1. Experiments and observations also tell us that the magnitude of the force depends on the distance between the two masses. Specifically, the magnitude of the force is inversely proportional to the square of the distance, where the distance is just the magnitude of the vector r. Now, we can combine all this together into a statement which says the magnitude of the force is proportional to the product of the masses divided by the square of the distance between the masses. The words "is proportional to" means there is some constant we'll call big G, such that the magnitude of the force is equal to G times the product of the masses divided by the square of the distance. G is called the universal gravitational constant. Universal because it's generally believed to apply to any pair of interacting masses. Big G has the value shown in the SI system of units. Now we can write down an expression for the full vector gravitational force. We write this down as the product of the magnitude and the direction. This is often called Newton's law of universal gravitation, which, as expressed here, is rigorously correct when both our system and our object in the surroundings are point-like. That is, the spatial extent of the masses is small compared to the magnitude of r, the distance between the masses. However, it can be shown that if one or both of the masses are spherically symmetric, that is, each mass can be thought of as being built up from layers of hollow shells concentrically nested one inside another, say like an onion, where the mass of each shell is spread uniformly on each shell, then this expression for the gravitational force applies as long as we take as the center-to-center spacing, the center-to-center distance between the masses as the magnitude of r. This result is useful in astronomical contexts as it applies to a good approximation to heavenly bodies such as planets, moons, and stars. So let's do an example from this realm. Let's say we want to find the gravitational force on a planet due to a star. And let's say we know the mass of the star. Now, as an aside, the form of scientific notation we use here for writing large numbers is the same form that we will use when constructing computer models. So we're going to practice that here. So let's say we also know the mass of the planet. And additionally, let's say that in some coordinate system, we know the position vectors that locate both the planet and the star. Now, as another aside, it's a good idea to draw sketches like we're doing here to help us visualize the problem we're solving. With this information, we will be able to apply Newton's universal law of gravitation to find the gravitational force of the star on the planet. We'll do this in a sequence of steps. In this problem, we're trying to find the interactions that could affect the planet's motion. So our system is the planet, and the star, the source of the force, is in the surroundings. With this in mind, we will need to find the relative position vector that locates the system with respect to the source of the force. See if you can do this. Here is the result where, for this problem, the vector r points from the star to the planet, and it is obtained by the vector subtraction r planet minus r star. Now, next, we want to find, or need to find, the unit vector r hat, which we will need to describe the direction of the gravitational force. See if you can do this. Here is the result. Notice to find r hat, we need to calculate the magnitude of r, which is the center-to-center distance between the planet and the star. We need this distance to calculate the gravitational force too, which we will do next. Now, see if you can put all the parts together to calculate this vector force, which is the product of the magnitude and the direction. Here is the final result. As a quick check, we should compare the sign of the force components to our sketch. The sketch suggests that for this coordinate system, both x and y components for the force should be negative to indicate properly the direction of the attractive force pointing from the planet toward the star. Our answer has negative x and y components, so that seems correct. One final note. Newton's universal law of gravitation can be used to find the weight force of an object near the Earth's surface. For an object that is at height y above the Earth's surface, the magnitude of the weight force is just the gravitational force on the object due to the Earth, which is given by big G times the product of the mass of the object and the mass of the Earth, divided by the square of the distance from the center of the object to the center of the Earth, where that distance is just the sum of the height and the Earth's radius. Now, if the height y is small compared to the Earth's radius, then we can ignore the height in this expression. And to a good approximation, we can write the magnitude of the weight force as the product of the object's mass times a constant, which is what we will call little g, the magnitude of the Earth's gravitational field near the surface. Now, we can see how we can find the weight force for that same object on another heavenly body, say a moon or another planet. We will just need to find the appropriate g using the properties of that moon or planet.